Let me start now immediately with our topic for this morning. This morning we will talk about resource efficient and cleaner production, focusing at the dairy sector. What is the idea of this resource efficient and cleaner production about? Basically, in a nutshell, it's about prevention. We have this hierarchy of activities, we have these priorities of our activities. We put prevention on top of everything. So this means that we look at the dairy from a different perspective, with slightly different spectacles, not purely from the point of operation, not purely from the point of getting the right product in the right quantities out, but also looking at the environmental impact, looking at waste, looking at emissions, looking at energy consumption, with an eye on identifying opportunities to reduce environmental impact by preventive measures, reducing waste and emissions in the first place, and at the same time saving, because less waste, less milk losses in the wastewater in the case of a dairy automatically means less raw material which we have to buy. If we avoid losses to the wastewater, we avoid monetary losses from our pockets at the same time. Same is true for energy. If we can reduce our energy consumption, not compromising the quality of the product, not compromising productivity, we can do something good for the environment, because we need to generate less electricity, we need to burn less fuel, and at the same time we save, because less fuel means less fuel we have to buy, less electricity means less electricity which we have to buy from the grid. So our focus, our top priority is prevention. What cannot be prevented in terms of waste shall be reused, recycled. I will show a few examples later on what can be recycled. Basically, as in nature, everything can be recycled, can be reused internally or within another company as a raw material. And only what cannot be reduced, what cannot be recycled, shall be disposed, shall be discharged to wastewater, shall end up in a landfill. So that this actually is our priority. We try to mitigate waste and emissions, we try to reduce waste and emissions, and we try to dispose of, to treat in the end only as little as possible. Our strategy is the following. Our program usually grows. We start simple. We try to identify what we call good housekeeping measures. Very simple measures which can be implemented right away without any effort, yielding immediate benefit. Good housekeeping measures here in this seminar room would mean last person who leaves the room switches off the light when there is no need for light anymore. Last person here switches off all these computers so that they do not continue to consume standby electricity consumption. In the company it would mean we switch off the water when there is no need for cooling anymore, when there is no need for cleaning anymore. These are the simple measures we are talking about when we talk about good housekeeping measures. Building on these measures, we would slowly start to adapt the technologies we are using. We will see quite a few examples later on to illustrate what I'm talking about. Technology does not necessarily mean new equipment, latest equipment. It's clear that latest equipment is probably more efficient than older one. But we also can operate older equipment in a better way by improving controls, by installing sensors, by optimizing control strategies. If we start thinking out of the box of our enterprise, we start discussing industrial symbiosis then, cooperation between companies, maybe regional cooperation to exchange energy so that waste heat of one company can be used in another one, that maybe refrigeration is used together, sharedly by more companies. And these all shall lead in the end to what we call eco-innovation. New products, new services, which will provide benefit for all of us, but at much less environmental impact as compared to today. But we start slow, good housekeeping first, measures which can be easily implemented within our existing production, and then slowly we adapt technologies. We will see examples in a short time. Now, what I would like to present with the next slides is an overview of typical processes in dairies, processing milk, and link these process descriptions to major environmental impact, to major losses, wastes, wastewater generation, major energy consumption, because then on these observations we will build the recommendations. And this actually is also the point then of this pocket guide, which was developed within this program to support the mainstreaming of all these ideas within dairies here in the region. Because this pocket guide then gives recommendations, suggestions, what can be improved to reduce waste and emissions in dairies, to improve environmental managerial practices in dairies, so that in the end we have less environmental impact and savings for the enterprises. So let's start running through the processes in the dairy industry, linking them to major waste emissions, and then we will discuss in the end what can we do to reduce waste and emissions in a profitable way. Milk processing starts with reception. Milk is collected from the farms, maybe in cans, maybe in trucks. It is delivered, it is received, quality is controlled, like the content in fat, like biological qualities. Milk is immediately cooled because it's a very sensitive material. The empty tankers have to be cleaned thoroughly. We will discuss this in a minute. Milk is probably clarified. Some solid waste is generated here. The milk will be filtrated. The milk will be separated to give the cream, to give the milk as a basis for standardization. Then the defined quality of the marking milk, which we want to have. Milk is probably pasteurized before it is packaged or processed to other products. Whether we process it to yogurt, whether we process it to cheese, whatever is our final product. Let's run through this using a few pictures so that we dig into what we are talking about. This here is a road tanker delivering milk to our dairy. The road tanker has to be cleaned. We all know that this can be done in different ways. A very simple approach of cleaning this road tanker would be a man enters through the manhole and starts rinsing the road tanker with a hose. This probably is a point for improvement, because this is not very effective operation, consumes lots of labor, takes a long time, and wastes a lot of water. We will discuss in a minute, it would be much better to link the cleaning of the road tankers to a CIP plant, where we recover cleaning solutions, use them for a long time, have the same or a better cleaning effect, but with much less chemicals, much less water consumption. We will go through this step by step. Next comes metering, because we need to know how much milk we actually receive. Next comes quality control, because we need to make sure that we are buying milk which is biologically safe, which is also rich in fat. Next step is cooling, probably a plate type heat exchanger, and the chilling unit working somewhere in the utility section. This consumes probably warm water, this consumes some chemicals, the chilling consumes electricity. This is a storage tank, day tank, holding the milk until quality control is finished, until the milk can be given into production. Also, these tanks at the end of the day require cleaning. Here we see a pasteurization unit. Here we have the bacteriophage. Also here, at the end of the day, we have to clean the equipment. The equipment also is consuming quite some energy in the pasteurization section for heating the milk, for holding it at the required temperature, for cooling the milk to storage temperature after pasteurization. This here probably in most dairies is the biggest consumer of heat. So we will deal with this pasteurizer in much more details, and I will show a few energy efficient solutions which can provide the quality which we need at the least possible expense for the enterprise. Here we see packaging material. Our dairy here, the example dairy, is using very simple packaging, simple bags for the milk. Packs from polythene, showing very nicely the logo of our company so that it's a good advertisement at the same time. These are the packaging lines. From the film, the bags are formed, the milk is introduced, the bags are soldered so that they are tight. Of course, we will have lots of problems here. Setting up the machine, running down the machine. There will be some breakages of bags. We will require cleaning all the time. So this filling operation will involve losses. We will discuss in a minute how to reduce these losses, how to minimize these losses. Because packaging material is expensive material. It's very dear material, and by proper setup, by smoothly running the machines, we want to minimize waste generated here. Ready product is stored in crates, moved through the company, moved to cold storage. Here we see a forklift driver, cold storage with the lights on, the cooling of the area. All this requires energy. So our focus in this refrigerated storage section, of course, will be energy efficiency. How to enclose the area, how to minimize air intake, which would require additional cooling. All these things we will discuss in a minute. Looking at the compressor, the chiller, biggest consumer of electricity in a dairy is cooling actually. Efficient cooling, therefore, is a focus of our suggestions. From describing the main process flow, I think it's very clear that cleaning is a major operation in a dairy which has an environmental impact because it's using water, it's using energy, it's using chemicals. Efficient cleaning, therefore, is a focus. An essential element of efficient cleaning is cleaning in place, our CIP plants. We have here simple example. It's 3 tanks only, holding the caustic solution, the acid then for neutralization, and the rinsing water. And the trick in CIP cleaning is not to prepare the chemicals once, send them through the equipment and then discard them, but to circle them through the equipment for a definite time span, then recollect, measure the concentrations of my active ingredients, top them up to working concentrations, and reuse them. So instead of using the cleaning solutions once only, they ideally can have a useful life of weeks or months, which at the same time means less chemicals consumed and less emissions to the wastewater. So what is good for the environment, less water for cleaning, less chemicals for cleaning, is good for the company because it does not have to pay for all these chemicals anymore. And wastewater treatment as the last stage is something with these big quantities of water consumed and the wastewater load a dairy usually discharges is inevitable. A dairy will have a boiler because we need hot water or steam for several purposes. We mentioned already the pasteurizer, which probably is the biggest consumer of heat, but also hot water for cleaning purposes will be a major consumer. Now to recollect all our observations, we look at the flow chart of a generic dairy operation. You will remember all the different stages from the description. We have the reception of the milk, collection in the holding tank. We have the testing in the laboratory, the checking of quality. We have the separation, where we separate cream and skimmed milk so that we can mix the desired concentration then, depending on my product. We have pasteurization, and we will discuss in a minute the structure of an effective continuous pasteurizer which recovers as much heat as possible and reduces the external heating requirements and the external cooling requirements. Then homogenization, the filling, the bottling, depends on the bottles we use. Can be PET bottles, polythene bottles, can be bags, can be glass bottles. These are basically the steps we were talking about. One important specific process is cheese making. In cheese making, all the solids basically are trapped in the curd, leaving the whey. The whey still is rich in sugars, still is rich in COD, in chemical oxygen demand. However, in many operations, whey is discarded. Whey is sent to wastewater because in the old days it used to be given away as animal food, Nowadays there is so much cheap animal food that there is no point in using whey. What to do with whey, we also will discuss in a minute, because it actually is a very valuable byproduct which we definitely should not discard to the sewer. So now, as we were looking at the flow chart, now the main environmental impacts out of our processes. We have here the flow chart depicting what we have discussed now a couple of times, the processes of dairy processing. We have the major input materials, which of course are milk, raw milk, but also energy, lots of electricity, lots of fuel, which are also detergents, sanitizers, which are refrigerants for cooling. And the environmental impacts are, of course, our products, which is a nice environmental impact, because so many people can enjoy our dairy products, the milk, the yogurt, the curd, the cheese. But we also generate byproducts, effluent, wastewater, containing all the milk which stayed as a residue in pipes, in tanks, because we did not fully empty them. As a residue from cleaning, all the small milk losses from spillages, all this is in the effluent. There will be some air emissions from our boiler, from the generation of electricity, and there will be some solid waste. And this is now the environmental impact which we want to reduce, because all these effluent, all these air emissions, all this waste is not our main product. Our company is there to turn input into useful output, into a product which we can sell. Our main intention is not to produce waste emissions, which we have to take care of, which we have to treat, which we have to landfill, which we have to treat in the wastewater treatment plant. So what we are discussing now is how to reduce these byproducts in a profitable way. Impact, to highlight a little bit, and also now to discuss a few numbers, to give us an idea about quantities, to give us an idea about benchmarks. Major impact of dairy processing, or a big impact, of course, is wastewater. Dairies consume a lot of water, mainly for cleaning, and generate quite some effluent. The main organic load in our effluent actually is milk. So actually the main organic load, the main contaminant, is a loss for our business, because it's milk which we could not turn into a product. Another impact is energy consumption. We have seen during our discussion that in so many places we need cooling, we need heating. Dairies are major consumers of energy. Solid waste also we do generate from broken packaging, from product which is not sold but returned to our plant because it over expires, for example. And of course there is some hazardous waste, probably mainly from maintenance, from changing oils, from laboratory maybe. Emissions to air is basically combustion gases from our boilers. A small topic, but still important topic, are losses of refrigerants, because still many refrigerants which we are using in our cooling equipment are CFCs, which negatively interfere with the ozone layer in our atmosphere, which destruct ozone layer and increase the amount of ultraviolet radiation which hits then the surface of the air. So the minimization of use of CFC and loss of CFC also is a side aspect of our activities. We will come to that shortly. Now I promised some numbers for orientation. Some remarks before we start jumping into numbers, because this is always the question: how much water does a good dairy consume? How much electricity is acceptable for a dairy? And before we dig into numbers, I have to say it depends. It depends on a few things. Let's briefly explore what has an impact on water consumption, on energy consumption of a dairy. Of course, a major impact comes from the cost of water. The most water efficient dairies you find in countries where water is dear. In northern Germany, for example, in Denmark, where you pay 4 or 5 euros per cubic meter of water and 6, 7 euros to treat 1 cubic meter of discharged water. Of course, people are very careful to use as little water as possible. And in countries where water is cheap, available almost for free, just for the cost of pumping and filtering it, of course there is less motivation to save water to the last digit behind the comma. So this is an impact we have to have in mind when looking into benchmarks, questioning where do these numbers come from, what is the background in these countries. A general number, a up-to-date dairy processing plant, average size, will consume somewhere between 1.3 to 2.5 liters of water per liter of processed milk. Now, this is just for orientation. 1 is okay. Good dairies can process the same liter of milk with 0.8 liters of water, and some even less. Let me show you some numbers. These are from the European Dairy Association. They are in your materials. They are in this pocket guide. There are other numbers which are collected by the European Commission by their joint research center in Seville in Spain when they compile the best available technology reference guidebooks. This table now gives us numbers a little bit depending on the product. So if we are producing drinking milk only, water consumption should be more below 1 liter per liter. If we are processing milk to cheese, to yogurt, to other products, water consumption will increase a little bit. But already in this table we see something, I'm sure you have noticed that. We have a minimum, we have a maximum. Now, what does it tell me if this table, which comes from the European Dairy Association, so which is a valid reference, tells me a dairy can consume, if it's very good, 0.8 liters of water per liter of milk, or can consume similar products, similar region, up to 25 liters. That means there can be a wide range. And what does this range depend on? Of course, on environmental management practices, of course, on technology, but also, and this is a very important observation, on the size of operations. Because especially in dairy processing, we see a very pronounced economy of scale. The bigger the plant becomes, the lower is the specific consumption of water. Now, looking at this chart, does this make sense? That a much bigger dairy in terms of water consumption is much more economical than a small enterprise? Yes, it does. Because the main water consumption in a dairy is not for the product, it's for cleaning. And cleaning I have to do at the end of the day or when I change product. So whether a dairy operates longer hours, produces more out of the same equipment, does not have so much impact on the daily water consumption. So the bigger production, the more continuous a process is in a dairy, the less the specific water consumption. And this is really important impact, because you see here, if the size of the dairy increases by 4 times, specific water consumption comes down from 6 to below 1 liter per liter, just because of frequency of cleaning operations. Now, what's the lesson to learn out of this? Lesson number 1, continuous production, as continuous as possible. Small example, small dairies which I know in my region, which of course process every day because cows give milk every day, stop producing yogurt every day. They concentrated yogurt production to 4-5 days a week and store the milk in between to reduce the frequency of cleaning of at least the yogurt lines. I mean, that's the same what breweries do. During winter, when not so much milk, not so much beer is consumed, they concentrate actual production on fewer days to reduce the need for cleaning. Small excursion out of this. Now, very similar considerations we can discuss for energy consumption. We will dig into these details very soon. Connected to water consumption, to wastewater generation, is the topic of milk losses. This is a really important topic in every dairy, to bring down milk losses. Because milk losses are not only inducing wastewater load and nuisance for the environment, but they are financial losses for the dairy. It doesn't make sense to pay the farm for milk, which I then dump into the sewer. This is a typical breakdown of milk losses in a mid-sized dairy. We talk about, as a benchmark, about more or less 1% milk losses. So this should be a relevant exercise for every dairy to closely monitor, to closely watch milk losses, and if possible also to get an idea where we lose the milk, whether it's in the cleaning operations, because it's residual milk which stays in the pipes, in the tanks, in the filling machines maybe, whether it's spills maybe, whether it's maybe overfills, because the capacity of the tanks doesn't match the actual demand. So to track milk losses, to get an orientation whether they are 1%, below 1%, or more towards the 2-3% is a really important exercise. Milk losses are connected to effluent. In the effluent, we will find all these milk losses, and this is a list of potential milk losses, which mainly are connected to spillages, to foaming of milk, to cleaning operations, to leaks from pipes, because the flanges are not tightly filled after reassembling the equipment. All these small sources of potential losses. Now, from a perspective of an environmentalist, the problem of milk losses is COD, is chemical oxygen demand, which the milk causes by its nutritional value in the wastewater. 1 liter of milk has actually a highly relevant chemical oxygen demand. We are talking about 210 grams per liter, not milligrams, not micrograms, grams. Milk is very nutritious. Milk is very strong food. So if we spill milk, we add a lot of load to the wastewater. And actually, it works the other way around also. From the COD, which we measure in the wastewater, we can calculate, at least we can conclude, the milk losses which we have in our dairy. High COD in the wastewater typically shows high losses of milk. So if the municipality is upon us because the high discharge of COD in the wastewater, this should ring an alarm with us also, because high COD in the wastewater automatically means high losses of milk. Of course, what we discussed earlier, the tendency towards bigger plants regarding wastewater loads also means better performance, because less cleaning operations typically mean less milk losses, mean lower specific COD in the wastewater. Now, just to refresh our minds and to alert us for potential losses of milk, where will we have to expect milk losses? Where typically do we lose milk? From the tankers, from the road tankers which deliver the milk, we might have losses because the tankers are not completely trained, because there are spills maybe. If we are using cans still, these 30 liter, 20 liters cans, during cleaning, there might be significant losses. Spills, leaks from hoses and pipes, spills from storage tanks. When we disconnect storage tanks, probably there are some spills. Foaming, if there is not enough headspace to contain foam, there might be losses. And again, during cleaning operations, if the pipes, if the tanks are not trained 100% before cleaning starts, there might be significant losses. Now, during pasteurization, where do we expect losses? Again, from leaks, again from cleaning operations, from foamings, and maybe some deposits on surfaces. Same during homogenization, basically in the equipment, losses in the equipment. During separation clarification, a very similar story. If the equipment is not trained properly before cleaning starts, there will be losses. During the bottling, during the filling, overfilling might be a loss poor drainage of all the connecting pipes, the machine before cleaning starts might induce losses. In cheese making, now the story starts. Overfilling vats can be an issue. Spills, leakages, cleaning operations, and then this is our next topic. The discharge of whey might be a major issue. Whey remains after cheese making, can be sweet, can be salty whey. Whey is 80 to 90% of the total volume, because most of the liquid actually stays in the whey. It holds most of the lactoses, about 20% of the protein, which results also in a significant COD of whey. Whey has a COD of 60 grams per liter, which is a lot. Takes a lot of water to dilute whey to a concentration which is manageable in a municipal wastewater treatment plant. So whey, wherever possible, should be recovered. We will discuss in a minute what could be useful byproducts out of whey, where whey can get good use. Energy consumption should be somewhere in these ranges between 0.2 gigajoules per ton to maybe maximum 2-3 gigajoules per ton. This line here is a specific one with a very high energy consumption. This is the production of milk powder. This means spray drying milk, which is very energy intensive. This is a dedicated process. This is not directly comparable to production of market milk or to the production of cheese or yogurt. Lots of discussions of the process of the use of water, use of energy. Now, the interesting part for us, of course, is what can we take for our enterprises? What are typically areas where we can improve? This part of the presentation goes by, we call it unit operations. So the different units and areas of production in a typical dairy in our case. We start simple. You remember our different approaches, our sequence of strategies. We start simple. First issue will be to talk about managerial practices, about best operational practices. In this respect, we will also talk about the management of chemicals, how to dosage chemicals, how to store chemicals, how to transport, how to manipulate chemicals in order to minimize losses, because this area can cause significant losses. Also connected to environmental management is measuring water, measuring energy consumption, dedicated to units, so that we know actually where we consume water for which purpose, where we consume energy for which purpose, so that we have starting points then, where we can apply best practices or where we can improve controls. The pasteurizer is a unit which consumes a lot of heat. That's why it gets due deliberation. CIP, cleaning in place, is a unit we definitely have to look into. Cleaning in general, like general cleaning all the the pipes, cleaning the plant floor, cleaning part of the equipment which probably is not linked to CIP plants is an issue. The boiler providing heat for the plant is such a unit operation. We will look into power supply, generators, air compressor, air we will need for packaging material, maybe, for packaging operation, maybe for some cleaning operations, for controls maybe. Refrigeration is a point of concern, packaging, waste separation, maintenance in general, wastewater, and then there are some minor issues which we will just touch, which is green building, so architecture, which helps, which assists energy efficient buildings, just small things to avoid the intake of heat through big windows in cold area. One example, a green roof maybe, to keep the area below cool would be such a point of consideration. Lights, because lights are everywhere. These are basically the points we want to dig into, the points for which we want to analyze a little bit deeper what can be done there to reduce energy consumption, to reduce chemicals consumption, to reduce the consumption of water without compromising quality of product, without slowing down production. Now, environmental management, what would be points of concern? Basically, the most important point is involvement, is proper training, is also to some extent monitoring and controlling. This topic very strongly is linked to, of course, proper training, and this starts from collecting material safety data sheets to provide information on chemicals. This involves standard operation procedures, giving proper set points, proper maintenance procedures to the operators, so there is a reference which can be used for training, best practices, but which also can be used for controlling then later on, for holding people responsible for their activities. Small questions maybe for the maintenance people, but also for the plant shop managers. First question goes towards works planning. Are we using the right equipment, right size of equipment for the right task? Can we have more continuous operation to avoid the frequent need of cleaning, avoid frequent stops, startups, so that we actually can produce continuously? Are valves, other pieces of equipment, points of control, set points, clearly marked, and do the operators know which valves to shut off, to stop water flow, to empty a pipeline completely, to stop compressed air from escaping when equipment is not using? Is startup and shutdown, specifically these two operations, which are not actually production and sometimes overlooked, are these sequences, are these procedures clear, and are operators trained what comes first, second, third? Also when shutting down a plant, which valve needs to be shut first, second, third, to minimize losses, to minimize the need for rinsing, for example. Are there trip pans to collect milk losses when opening flanges, for example, to prevent them from entering wastewater? Looking at storage of chemicals, does our chemical storage look like more the picture on the left-hand side or more like the picture on the right-hand side? This is not a dairy, this is a small chemical company. In this chemical company, they lost 7% of their chemicals just in storage. 7% of their chemicals were never used in the processes, but they were lost because bags broke, because the forklift drivers cut bags, pallets broke, and this unidentified mixture of chemicals had to be disposed of. You cannot use these chemicals. You cannot identify what it actually is. So to have clear storage procedures, to have good separation of alkaline media, of acidic media, to have drip pans, to collect any spills and so on, should be part of our activities. I mentioned already a very important instrument of environmental management. In a dairy we will use chemicals, we will use detergent, we will use acids, we will use caustic soda for cleaning and so on. So we need information on these chemicals. This information is contained in the material safety data sheets. These material safety data sheets give us an idea what actually is the chemical we are dealing with, what are the properties, are there any hazardous properties, what are first aid measures in case there is an accident with the chemicals, what do the operators have to know about the interaction of this chemical with the environment, what do they have to do in case of spills, in case of a fire. All this information is in material safety data sheets. So if we do not have this information at hand, how shall we manage chemicals? This information needs to be in-house, and this information needs to be processed. Operators need to be knowledgeable about the materials they are working with, and they need to be trained for spillages, for accidents with these materials. And of course, in proper using them. Right dosages, right set point, right concentrations. Next topic, they need to have also the right instruments to dosify. Many times when talking to operators, I've heard, well, dosification. A little bit more is always on the safe side. This is not necessarily true. We will discuss this in a moment when discussing proper dosification of chemicals for cleaning. For many applications nowadays, we have automatic dosification equipment for a bottle washer, for CIP plant. Not to leave it to the operators how much they add, a little bit more, a little bit less, but automatically to add exactly the volume of chemicals it takes to have the best possible result. All the time, always, not depending on day shift, night shift, weekend, personal ideas of the operators, always same concentrations automatically. This is quite standard actually for all bigger installations. Many major suppliers of chemicals have started to supply this dosification equipment at no or very low additional charge to make sure that you're using their chemicals in a proper way. Because, we will discuss this in a minute, some chemicals, if you put more. They don't work better, but worse. There are optimum concentrations for many chemicals. This information we need from the supplier, from the technical data sheets, which need to be processed, which need to be known to the operators. Water, also, there should be rules, there should be procedures. How much water can you use for cleaning? In order to monitor water use, there need to be meters. If there is only one water meter for the whole plant, it's very difficult to attribute where the water goes. So for the major equipment and for cleaning, so maybe for the CIP cleaning plants, maybe for general cleaning, there should be dedicated meters. Can be very simple turbine meters, which are read on a daily basis, or in a bigger plant can be nice automatic meters, but definitely there should be 3, 4, 5 sub-meters for water to be able to attribute water consumption to individual units, to individual areas. Couple of times we already mentioned a key. If you think about the graph in the beginning, rating water consumption to size of operations, we should aim for continuous production, not frequent changes if possible, but continuous production, reducing the need for cleaning. The automatic cleaning, we discussed already. The CIP cleaning, details will come in a minute. Avoiding milk losses is a major issue. I have reiterated this a few times, but this really is part of day-by-day management. In order to assist us, I will present a brief example later on. Optical sensors can help. Turbidity meters in the lines can help to identify until when there is still milk in the line and when clear rinsing water starts. And these automatic sensors can help us to prevent milk losses in the first place, but also to minimize the requirements regarding rinsing water. I will show an example in a minute. Label controls to avoid overfilling tanks, which might be a little bit too small, should be standard practice. Automatic shut-off should guarantee that there are no losses from overfilling tanks, from milk running when the volume of the equipment is already exhausted. In cleaning then, we have a few rules. One central element of cleaning is mechanical cleaning. We will discuss also in a minute this cleaning diamond, these effects, these variables we have for effective cleaning, which are basically the use of chemicals, which is the use of temperature, and is the use of mechanics. And effective cleaning, cost-effective cleaning is connected to high pressure. We will discuss this in detail in a minute. Recirculation of water wherever possible for cleaning trucks, for watering the greens, for such minor purposes is also a standard practice. And the topic of foam cleaning is also a topic which we will discuss in a minute, to allow time for chemicals to penetrate contamination, to work on the floor, on the wall, before we rinse them off by foam cleaning. is a very effective approach. Now let's start. What I want to show first is unfortunately without sound. This is not advertising anybody. This equipment is available from many other companies, many other suppliers also. This supplier just put a nice video on YouTube to show you. So this is pre-cleaning now, pressure washing, using high pressure, low flow to mechanically remove contamination. Next stage, application of detergent, but as a foam, so that the detergent has time to impact on the surface, to penetrate contamination. Then rinsing, now with a lower pressure, because there's no need for high pressure. We need to take away the detergent in the foam. Equipment is a pressure generator. We can change the lancets depending on the angle, depending on the pressure which we want to induce. This foam cleaning is a really important element of effective, cost-effective, time-effective, low chemicals consumption cleaning practices for general cleaning, for cleaning difficult equipment which is not connected to a CIP plant. With these procedures, we have experiences reducing consumption of chemicals by 40% with the same or even better cleaning effect, and reducing water consumption by 70–80% for the same or even better cleaning effects. Yeah. This is available as small mobile equipment, but also as a centralized pump station with satellites which you can connect to this system. But basically the logic here is high pressure and time. So the use of foam to allow for time for the chemicals to work on the contamination. Let me go back now. Now, after this technical side, let's come back to a very practical side. Okay, last slide, then time for a break. Small example, long story. This comes from my hometown, city of Graz in the south of Austria, small city, 300,000 population. We used to have a dairy collecting the milk from our region. This is history now for the last 5–6 years because of all this concentration in Europe. Now we have 2 big dairies only for the whole of Austria, not 7–8 anymore. In this dairy, the dairy was founded in the 1920s or so, and then for 80 years they worked in the same location. They changed lots of things in these 80 years. They expanded significantly, they introduced new equipment all the time, they moved out all the old equipment. What they never did was to modify their piping system. So when we started working with them, they had lots of old pipes which had dead ends, which were not leading to any equipment in use anymore. But all these pipes had to be cleaned because they were at some points connected to pipes carrying actually milk, to tanks, to vats for yogurt production, to filling lines. We did an inventory. In the plant, they had more than 2 kilometers of lines which were not used anymore. So, the conclusion of the director was, all these pipes, all these 2 kilometers are linked to our regular pipe system. So when cleaning every day in the evening, we have to clean these 2 kilometers of pipe. This does not make sense. So let's cut out all the pipes which we do not use anymore. That's what they did. And cutting out these pipes right away saved 15% of the total water consumption. Just by taking out something that was not used anymore. Small example, but this is what we mean with these good housekeeping measures. Just doing things the right way the first time we do them. In this case, cutting out the pipes. To start with, I have here 3 questions from the first session. One was from Nunes regarding the contents actually of milk. Thank you. Sergei is giving me the accurate numbers. It's just my eyes are too weak to read that. But milk is very rich in lactose, about 5%. Lactose basically is a sugar, is a hydrocarbon. So it will show as COD, as chemical oxygen demand, because both the carbon and the hydrogen consume oxygen in the reaction. 4% of milk is protein and about 4% is fat. Also fat and protein is hydrocarbons. So when we react them with oxygen, they will consume oxygen because they will react to carbon dioxide and water. So fat, protein and lactose cause the COD of milk in wastewater. Then there was a specific question regarding chemicals, regarding replacement of caustic. I will check the specific Axonia you were suggesting. Basically, the basic cleaning we mostly still do with caustic soda. I will show a few slides on concentrations and so on shortly. And coming to Ian's question, who was asking whether this high pressure equipment, which could be seen in the video on cleaning, is comparable to conventional high pressure cleaners as they are provided, for example, by Kircher, without advertising them, just because this yellow color is all over the place. Yes, basically we are talking about the same. Kircher is probably the biggest producer of mobile high pressure equipment. In the video we saw both types, both the mobile one and the stationary high pressure pumps, which connect to a satellite system of hoses for cleaning them. So high pressure is something we strongly advertise. To continue from here, in general cleaning, very frequently we have the problem we are cleaning using open hoses. What is the problem about hoses? Usually there is no valve on the hoses, so whenever there is a break, whenever the operator stops cleaning for a while, he will put down or she will put down the hose, but the water will keep running. To prevent this, we use these spring-loaded trigger valves. So when the operator releases the handle because he or she doesn't use the hose anymore, automatically the water flow will be stopped. There is no excess use of water. This equipment is inexpensive. It starts at 10 euros a piece, goes in a professional die-cast version maybe to 30 euros per piece, but it can reduce water consumption for manual cleaning by 30% easily. CIP cleaning, how does it work? We discussed earlier the 3 tank system, with one tank holding the caustic, one tank holding the acid for the second cleaning cycle, for the neutralization of the caustic and the rinsing water. Basically, it works the following. This here represents the tank or the vat which has to be cleaned. We have here spray nozzles from which the cleaning solution is sprayed inside the tank. So no manual cleaning with a hose, but spray heads, high pressure, rotating, acting upon the surface of the tank, and the cleaning solution then is collected again in a tank. And at the end of the operation, the concentration of caustic or acid is measured, and the cleaning solution is topped up exactly to the concentration of chemicals which we require and is reused. Some of these cleaning solutions can stay for weeks or sometimes even months. The principle is reusing the cleaning solution. The steps in cleaning in place usually are a little bit more complex than in the simplified chart which I just showed. Usually we have pre-rinsing. So when the product has been drained from the vats completely, we have a first wash with water. For this first wash, we can use the final rinsing water then. I will explain in a minute. After this pre-rinsing, which basically takes out the residual product which still might be in the pipes, in the tanks, we use alkaline cleaning. Classical cleaning with caustic. After that, again, rinsing. After that, acid cleaning, which mainly removes the milk stone and neutralizes the caustic. And then this last rinsing stage. The water from the last rinsing stage usually is recollected and used then for the pre-rinsing, because the water for the pre-rinsing doesn't have to be very clean, because it will be contaminated with product anyhow. So cleaning in place means this sequence means that in each step the solution is recovered and topped up to the required concentration. We already mentioned the importance of high pressure in cleaning. These are the forces which we have at our disposal for effective cleaning. This here represents the contamination on the surface of a pipe, of a tank. And the forces we have are chemical. This is usually what we are using. Strong detergents, strong chemistry. We have temperature. Usually, with some exceptions, usually higher temperature means more effective cleaning. Like when washing our clothes, when we have really awful stains, we put the temperature higher. We wash the shirt at 60 degrees instead of 40. And we have mechanical force. When we wash the shirt, we can rub stains. Will help to get rid of the stains. And in modern cleaning, what we do is a little bit less chemicals, because it's bad for the environment and a cost. A little bit less temperature, because also temperature is energy and is cost, and more mechanical force, more impact on the surface. Because this is effective and comparatively, in comparison to temperature and chemical force, it's cheaper. And this is the logic behind these high pressure cleanings, and this is the logic behind these high pressure rotating spray heads, which are built into tanks for cleaning. We will see a video shortly. Now, regarding chemicals, regarding parameters for cleaning in place plants. Mechanical force also means velocity of cleaning agent, velocity of the water, velocity of alkaline solution, and so on. This should be in the range of 1.5 meters per second. So it's actually quite fast circulation. Caustic concentration, usually optimum, is between 0.5 to 2%. And with the caustic, the thing is, more caustic not necessarily means more effective cleaning, because in the boundary layer, close to the surface of the vessel or the tank, with the concentration of caustic, also viscosity increases. So the cleaning effect becomes actually worse. This is an experimental curve here from one of the suppliers in Austria of cleaning materials. It shows the cleaning times versus caustic concentration. And we actually see that in these experiments there was an optimum at 0.5% sodium hydroxide. Below, cleaning effect was less. You needed to allow longer time. But above this optimum, the same was true. So at 1% or 2% caustic, cleaning time actually would have increased in comparison to the optimum. So this is an important observation, because there is such an optimum. More concentration not necessarily improves the cleaning effect, and this is a strong advocate for this dosage equipment, so that we actually stick to the optimum concentrations and do not allow more or less. Nitric acid, now for neutralization, 0.5 to 1.5%, comparable logic, temperature 60 to 80 degrees, depends on many factors. Mostly is determined empirically where the actual optimum temperature is, and time 20 minutes if everything is perfect, up to 60 minutes if the equipment is more complicated, the pipes are longer, and so on. But to start optimization, this can be a guideline for parameters of a CRP plant. One thing I was mentioning is in rinsing, already in pre-washing, but more importantly in rinsing, it's important to know when there is still milk and when there is pure water. In the old days, there was a looking glass, and the operator visually would identify in pre-rinsing when is there milk, when he can detect some turbidity, and when pure water comes, and when he can switch off the rinsing because it's completely clean. The modern instrument are sensors, turbidity meters or conductivity meters, which tell me from the turbidity when is there milk and when is there a clean front of water, so that I can stop the rinsing process, or when is there still conductivity, meaning alkaline solution, so rinsing has to continue, and when I can stop rinsing. These sensors are very reasonably priced. They start at a few €100, and they really can have an impact on water consumption and on product recovery. Let me show you in this respect. No, this does not work. Let me show you these two videos. Sorry about this interruption. This video now is on turbidity This shows how a turbidity meter is working. This is the sensor, this is the scale, these turbidity units. And the guy started with clean water, and now he's adding drop-wise milk, and you see how the sensor reacts. So it instantaneously detects turbidity caused by milk in water, so you can use this sensor very effectively to discriminate the milk front in a pipe from water front. So let's go back to this. And this video is an important one. No advertisement for Alfa Laval, but Alfa Laval you will be very familiar with. This shows such a rotary spray head, which is built into tanks for internal cleaning. This is 10 times more effective as compared to manual cleaning with a hose, because the rotary impact of the high pressure spray jet has a very high cleaning effect on the surface of the tank, of the vessel. Excursion on the other side now, is this effective? In a dairy you will use crates to transport products and so on. Crates need to be washed. Crate washing can account for 15, almost 20% of the water consumption of a bigger dairy. This is not effective. To have an open hose, to use some manual cleaning. Better approach is an automatic crate washer, where the crates are washed in a countercurrent flow of water. Fresh water is only used at the clean end to give the final rinse to the crates, and then the crates are washed in a countercurrent flow of water, and the dirty water actually interacts with the dirty crates. This can reduce water consumption for crate washing by 80%. Small excursion. What we see here on the left-hand side of this slide is the following. Actually, it's two things. One thing is, we discussed about measuring earlier, to use a few meters, sub-meters, to be able to attribute water consumption to different areas. In this case, the crate washer would be such a water-consuming area. A method which I'm personally strongly advocating for measuring water flows is this bucket and wristwatch approach. For two reasons. First of all, it's very simple. We do not have to install a meter. We do not need to have an expensive ultrasonic clamp-on meter. We just need a bucket and a wristwatch. And the data which we collect, like these, are quite accurate. We just measure the time it takes to fill the bucket, and then we know how much water flows out of the hose pipe, out of a valve, whatever. And the second beauty of this exercise is that it's very good to create awareness, because it's a visual exercise, and people doing this exercise will remember how much water there was in which time interval. So this looks very antique, ancient method of measuring water flows, but it is effective, gives good data, and is good for awareness raising. Last remark regarding this: what this gentleman is measuring here actually is the flow of condensate. To measure steam flow is difficult. A steam meter is expensive, but the steam, when it condenses after heating in this grate water, the washing water, it condenses, and condensate is basically hot water. And hot water flow is easy to measure. Don't need expensive equipment. I measure the same quantity, and then I can calculate how many liters of condensate were how many cubic meters of steam to heat my equipment. Now, in a big dairy, we will have road tankers bringing in the milk. In smaller dairies, we maybe have cans, and manual washing of cans can consume a lot of time and a lot of water. The better solution is an automatic can washer, or semi-automatic, which is basically rotating brushes. Again, no advertisement, there are lots of suppliers for this. A milk can scrubber. Rotating brushes, outside, inside. The can is immersed here around the center brush, and then it acts from the inside, from the outside. Can is clean with very little water, and no need for an operator to interfere with this operation, to do manual scrubbing and so on of the interior of the cans. This even can be made basically from a skilled maintenance mechanic. Let's continue here. Now, these were a few examples what can be done in cleaning, from manual cleaning, high pressure, CIP plants, optimization of CIP plants. Let's look at the case study. This is a company in Colombia. Colombia is quite industrial, actually. One would underestimate the industrial level they have. We are looking into a dairy which is called Fresca Leche, which obviously means fresh milk. And they produce about 50,000 tons of drinking milk per year, have some 100 employees. What we see here is their water consumption. This chart shows the specific water consumption, liters of water per liter of processed milk, and obviously over time. Starting point here was when they were engaging themselves, involving themselves into these resource efficient and cleaner production activities. Their water consumption was about 5 liters per liter of milk. Now, according to the benchmarks which we discussed earlier, it is not really good, but not too bad. So they were somewhere in the range. But when they started to digging into their cleaning practices, optimizing manual cleaning using these spring-loaded valves on the hoses, optimizing their CRP plant and so on, over a period of half a year, they reduced their water consumption to about 2.5 liters per liter, which is not bad. Now, you notice this line here at 1 liter per liter. What is this line showing? This chart here was used by management. They put it in the meeting room where they did their daily production meetings. And this chart was on the wall, showing the actual consumption and with this line showing the goal. Because they knew from similar discussions like we had this morning that it's possible to process a liter of milk with 1 liter of water. So they made this their goal. And I don't have the corresponding chart, but a year later they were there. They actually managed to reduce their water consumption to 1 liter per liter of processed milk. So by applying all of these, by installing also this communication, this feedback with the operators, to invest some time into training, into monitoring, controlling, they really managed to bring down their water consumption from 5 liters per liter to 1, which is quite something. I think we agree. Now, let's skip this. I mentioned earlier, and I think we all are aware of this, that a main consumer of heat in a dairy is pasteurization. Because we need to heat the milk to, depending on the process, 67, 72 degrees and hold it there for 7, 10, 12 minutes and then cool it down again to storage temperature, which will be around 4 degrees, 5 degrees maybe. So we need to put in heat first and then remove the heat again. Now, if we do this in a batch process, this means heating and then cooling. So all this heat is wasted, and additionally we need a chiller for cooling. In a continuous process, in this plate type heat exchanger, the process is done in a countercurrent way. So this is heating here. The milk is held at the target temperature of 72 degrees for the required time. But then the outflowing product milk in a counterflow heats the incoming milk. So that big part of the heat which is stored in the product milk preheats the incoming milk. And ideally, after that, I have two-stage cooling. First cooling is done by water, well water at 10, 12 degrees, to take the temperature of the milk down as much as possible before cooling with chilled water or ice water starts, which will take down temperature of milk then to 4 degrees or so. Why do I have two-stage cooling? Because the cold brine or the ice water is much more expensive than well water. So I try to remove as much heat as possible with a cheaper cooling medium, the cold water, before I used chilled water or ice. So a modern continuous pasteurizer can be very heat effective because of this heat recovery, and can be effective for chilling because of this two-stage chilling. Chilling with wastewater, with well water, and then using an electric chiller to bring down the temperature to the desired temperature. Again, this in a video. This is now continuous pasteurizer, and this is showing these sections. The heating section, heat recovery, and cooling section. So the hot milk, when flowing out, heats the incoming milk. And the important thing here is this section for heat recovery needs to be big enough, because in quite a number of installations which I've seen, people try to economize the initial cost for investment, and by saving plates in the heat recovery section, they wanted to bring down the initial investment cost. This is saving on the wrong end. This heat recovery section needs to be big to recover as much heat as possible, to avoid excessive heat for heating and additional cold for cooling. So, if possible, and in bigger installations, this definitely will be the more economical approach. Pasteurization should be done as a continuous process in a plate type heat exchanger. And this plate type heat exchanger has three sections, one for heating, one for heat recovery, which should be sized properly, and then a section for cooling. And of course, again, our old topic, which we have discussed a couple of times today, pasteurizer should be operated continuously. If possible, no stops during the day, no need for additional cleaning during the day. So this is a challenge for production planning, to use the equipment as continuous as possible. Storage temperature then depends on the product. We mostly use about 4 degrees. And again, to reiterate, main losses in this area will be spills, will be mistakes, will be pipes which are not drained properly before actual cleaning starts. And coming back to Nunes' questions, spills, all the milk which is introduced into the wastewater means additional proteins, additional fat, additional lactoses, which is lost as a product and which enters wastewater, causing CO2 there, which needs to be removed in a treatment plant. Yeah, solid waste, actually in a dairy there should not be much. If we are using glass, glass can be recycled. Packaging material, it should be possible to recycle it or to use it in an incineration plant or something. And if there is paper waste, cardboard waste, it should be possible to recycle this 100%. In storage of milk, the main issue becomes chilling, cooling, refrigeration. And there are a few topics there which are important in cold areas, cold warehouses, which is good insulation, 15, 18 centimeters of polyurethane panels are good insulation side. Doors should be closed, if possible. There should be PVC curtains, lamella curtains, because we could do these calculations. I think all of us would underestimate how much heat you introduce to a cold storage if you allow free circulation of air. Good maintenance, we will discuss in a minute. This includes defrosting in really cold areas. This includes cleaning condensers to allow air to take away the heat from the compressors if we do not recover the heat. And in bigger installations, ammonia is a very efficient refrigerant. We also could do these calculations. Thermodynamically, ammonia is a very good installation. If you do proper design, keep the volume of ammonia in your system low, ammonia can also be a very safe system. But we will discuss about refrigeration in a minute. Now, as we talked about milk losses a couple of times, in cheese making, corresponding loss can be a whey loss. Whey very frequently is dumped to the sewage system. In the old days it was used as animal food. Nowadays there is not so much value in animal food. This is a small example from an Austrian company who really analyzed the problem and who found a very creative solution and also very profitable solution. And this is maybe a starting point where also we can generate one or the other idea. In Central Austria, this is a dairy who is actually famous for their good cheese, seasoned cheese, like this mountain cheese, almost like Swiss cheese. And that's their product, and that's what they produce, and that's what they sell. Whey was a byproduct. Whey was discharged because the farmers were not really happy in taking the whey as animal food. Transport, cleaning the tanks, having trucks running around was not really a nice thing, so they dumped it. But the dairy grew, and that one day the mayor of the city said, well guys, your whey is in our wastewater, we have to treat the wastewater, this is a lot of cost for us, can't you do something about the whey? So the dairy started thinking about doing something with the whey. This was about 20 years ago when all these healthy movements started. So their product designer said, well, okay, let's take the whey, let's sell it as a healthy drink. So they put it to bottles, they tried to sell it, and it did not work. Nobody liked to buy and drink whey. So, problem, did not work. But these guys did not give up. They sat together and they continued working on the problem. And first thing they found out is, well, whey tastes a bit flat, not really exciting. So they decided to add nice aromas, like from maracuja or mango, first thing. Second thing, a plain bottle with a grayish drink does not look very appealing. So they decided to change the packaging. Nice packaging, sun, looks very healthy. And you know what happened? This became a hit. They sold half a liter of these for 1.5 euros. That's almost more than they got for their cheese. So they became really big in this whey drink. So the byproduct actually for a while brought them more money than the actual product. So there is gold in waste. Sometimes you have to continue working and really make something out of the byproducts. This will not be a universal solution, but for this company it worked out very well. Whey can be processed into quite a few things. In Italy, they acidify the whey and they process it to ricotta cheese, like it or not, but in Italy it's used a lot. Fruit drinks, there are quite a few variations of this now. In cosmetics, you need whey powder then. You can use it for the production of lactic acid as a biopolymer, like some of these plastic bags, which you can compost, are made out of lactic acid. You can still use it as animal food. You can process it to biogas. So there is some potential in whey. Actually, whey, if you spray dry it, whey powder is an ingredient in many bakery products. So there's quite a few applications for whey. Energy. Energy, again, let's start simple. You remember the second slide with our arrow starting from good housekeeping options, taking us the way through technology to innovative products and processes. Switch-off programs are very basic. We started discussing who will switch off the lights when we leave here, who will switch off this equipment. Same in the company. Who switches off the lights, the pumps, the fans, all this equipment which is running, maybe idle, maybe at the end of the day, air compressors, water pumps, all this equipment. Improved insulation of cold storage. Sometimes buildings have been expanded, floors are not insulated, the roof is not insulated well. Many plants, there is a lot of potential in better insulation of the facilities, but also of pipes. Pipes carrying chilled water as well as pipes carrying hot water. Steam pipes sometimes are not lagged properly. Valves, flanges are not lagged at all. Maintenance to keep energy efficiency of equipment high. Preventive maintenance on motors, on bearings, is something to think of. Talking about boilers, which we will do in a minute, combustion efficiency, air-to-fuel ratio is something, exhaust gas temperature is something to watch. Elimination of steam leaks might also be an issue. Just for your information, a cross-section through a boiler. How does the boiler work? Boiler combines fuel and air. The flame releases heat. The heat is transferred to water, if it's a hot water boiler, or to generate steam. And the exhaust gases then leave the boiler through a chimney. So where can there be losses? Obviously, if the ratio of air to fuel is not optimized. this might be a source of losses. If I have not enough air, combustion will be incomplete. Result will be soot depositing on the pipes, increasing resistance to heat transfer, inducing higher exhaust gas losses. Scaling on the tubes might be an issue. If the water is too hard, the hardness will precipitate on the tubes, will increase heat resistance, will increase losses. In steam boilers, an issue might be return of the condensate. Condensate is hot water, 100 degrees hot water. If we dump it, we dump all the energy it takes to heat the water to these 100 degrees. So condensate should be returned to the boiler as feed water. These are, in a nutshell, the most important points to look at. Now, a few observations, a few examples to look at or to memorize when looking for optimization potential. Here we are in a quite good boiler house, actually. They have automatic control of air to fuel ratio. So they measure residual oxygen in the chimney and they control the airflow accordingly. This is the controller. This is the indicator on the controller, showing the concentration of oxygen in the exhaust gases. Now the ones in the front rows can read what the display shows. This indicates 22.9% oxygen in the exhaust gas. Is this possible? Is this feasible? The air we are breathing contains 21% oxygen. So this probe apparently needs calibration. It's not only about the nice equipment, the sensor, the controller, the frequency controller on the ventilator, but it's also about maintenance. And it's about awareness, because an operator should have recognized long before that actually the indicator was faulty and probably the control was not working. So technology cannot replace well-trained operators which are well aware of what they are doing. Another example here, this is a hot water boiler. It's operating on natural gas. Water temperature is about 70 degrees. This here is the chimney, and this is a temperature indicator in the chimney. It has two scales, one in Fahrenheit and one in Celsius. And if we look at the indicator, we will recognize that the temperature reading is 250 degrees Celsius, which indicates that there is something wrong, because this temperature is much too high. This boiler was analyzed. The reason or the problem was they were using quite hard water. They had a water treatment plant to soften the water, but this was not working. So the hard water was constantly fed into the boiler, and there were deposits on the tubes, increasing resistance to heat transfer. So the efficiency of the boiler was coming down. Again, the indicator was there, but for a year or more, nobody had looked at the indicator. So technology is one thing, but awareness, monitoring, controlling, repairing is another thing. Of course, this was fixed immediately. The water treatment plant was repaired, temperature came down to 120 degrees. Now, difference of 130 degrees means 6-7% less fuel for the same benefit. How do you like this picture? Showing a heat exchanger, showing some scaling, some deposits. How long does it take until a heat exchanger has deposits like that, even allowing very hard water? Apparently, maintenance people had not looked into their equipment for months or years. So good maintenance is a really important issue also in a dairy, because this of course is not true for dairies only. This is true now for any industry. Our topic was condensate return in the dairy when you generate steam. After the steam has heated something, hot water in the pasteurizer, condensate will form, which should be returned to the boiler. Why? Because the condensate still, depending on the pressure level, contains 7 to 12% of the heat it took to provide this steam. So by dumping the condensate, we are sending away 10% of the energy which we put into the boiler. And how much does it cost to build a return pipe to the boiler house to collect the condensate and to reuse it as a feed water? Usually these measures pay back in 4 months, 6 months, for sure less than a year, because we are all paying more or less very similar energy prices. So this logic works globally. The operators had recognized what was the heat content of the condensate which they discharged. This is the same sewer into which we discharged the condensate a few meters downstream. And you see what the operators did? They put a bucket and their lunch boxes to heat the lunch, because they had recognized how much energy there was in the hot water which was discharged. After the condensate had been returned to the boiler, the operators got a microwave to heat their food properly in exchange. Yeah, there are numerous examples. This is a steam manifold distributing steam. This is about 4 meters long, half a meter in diameter. Heat losses here were a little bit more than 30 kilowatts. Insulating these pays back in half a year. Again, the operators were well aware of the heat escaping from this manifold. They prepared their tea on this manifold. Yeah, automatic purging, we are now getting into details, because in a steam boiler, every now and then we have to purge, because some hardness, some salts will accumulate in the hot water tank. Purging frequently is done manually. The operator every hour or so for 2-3 minutes blows down some hot water. The much more economic variant is to install a conductivity sensor and to have automatic purging, keeping the conductivity in the water at say 3,000, 4,000 microsiemens, and only discharging water, hot water, when there is a build-up of salts in the boiler. Here we are checking condensate traps. because when steam heating, we have condensate traps to separate the steam from the condensate and allow only condensate to flow through the return pipes to the boiler, keeping steam to heat wherever I want it in the heating coils or heating jackets. We are checking here whether these condensate traps work, because after a while, say 2-3 years, they will fail and need to be repaired or replaced. We're jumping now a little bit, jumping to compressed air, because also in the dairy we will use some compressed air, maybe for control of valves, maybe for packaging machines. It's just small observation in this case. Operator here is using air to clean his gear. It is not really effective, and it's even dangerous, because if you hit your ear with 6-8 bars compressed air a couple of times, you will lose your hearing ability. Better solution is a vacuum cleaner to clean off dust and so on. Much more effective than compressed air for cleaning. Seriously, usually in a compressed air system, most of the savings can be expected from locating and eliminating leaks. Before we start discussing exchanging a compressor to a better compressor or upgrading controls, let's look for leaks. Because in many systems, and some of the German suppliers of air compressors did studies in this, 40 to 65% of air actually are lost through leakages. So this is a huge potential to very simply, in a very simple way, save energy, to identify and seal leaks. A small leak, 1 millimeter, is big enough so that they can hear air escaping from that leak. Will cost me, if it goes unaccounted for a full year, depending on the electricity prices now a little bit, between 300 and 500 euros for electricity for the compressor to produce the air which escapes through this small hole. And 1 millimeter is the smallest hole I can identify just by listening. For smaller holes, I need ultrasonic equipment to identify. So to check the plant when it's down on a Saturday or in the evening when operations have stopped, to mark leaks and to seal the leaks is really a profitable exercise usually. This is the table then for your reference, what the diameter of a hole is, what the loss is, in this case calculated for 8 bars, and what the cost is, the associated cost for energy. Now for compressors, and we will discuss analogous situation then for refrigeration compressors. Actually, an air compressor is a heater, basically. Who of you is cycling every now and then? Riding a bicycle? Have you had to repair a flat tire recently, a puncture? And to inflate the tube afterwards with a small hand pump? What happens to the pump very quickly? It will get very hot, because this is an intrinsic property of air. If you increase the pressure of air, it actually increases the temperature. 90% of the energy you use to compress air actually becomes heat. is not stored as increased pressure, but is heat. So an air compressor requires a lot of cooling. And in a typical screw-type compressor, the heat is removed through the oil, which is circulating, and then through a radiator to the ambient air. The better approach is to use a shell and tube or a plate-type heat exchanger in the air circuit to heat water at first, to recover heat as hot water between 60 to 70 degrees, which is very nice for cleaning, many purposes, or for sanitary water, and only take the surplus heat, which we cannot use, which we cannot recover, to the radiator. So actually to reuse the heat from the compressor for heating. This is really effective, pays back to maximum 3 years. Now, biggest consumer of electricity in a dairy, some 60-65% of electricity in a dairy are consumed for chilling. This shows quite modern screw-type compressors. What are issues there? Issues we should be aware of. First issue is the type of coolant. Not sure whether we need to discuss R22 still, but actually these should be phased out, should be replaced. There are alternatives available from a thermodynamic point of view. A bigger chilling plant should run on ammonia. So whenever we are rebuilding, whenever we are expanding, we definitely should at least consider ammonia. There might be some restrictions, but basically from a thermodynamic point of view, ammonia is what we should choose. Some practical hints for saving energy with refrigeration. Refrigeration becomes effective if I can increase the temperature of cold. So if in a cold storage I need 7 degrees, I should not go for 6 or 4 degrees, because every degree I allow less cold temperature comes at the cost of 4% of electricity. So as a rule of the thumb, if this room was air conditioned, setting the set point to 18 degrees instead of 25 would cost 30% of electricity, more or less. So every degree I can increase the temperature of cold saves about 4% energy. Small thing, but can add up. So let's choose the adequate temperature. Let's not go for the least temperature possible, but for the adequate temperature. A clean condenser allows a good heat transfer, reduces the temperature of condensation, and has a very similar effect to increasing the temperature of cold, because it will reduce the temperature of condensation. So cleaning the condenser frequently or regularly will reduce electricity requirement. Storage rooms should be used to their full capacity. It's better to use one room at full capacity than 2 rooms at half capacity each, because we can switch off one and we do not induce all the losses from the surface area, from the roof insulation, from the bottom, from the air circulating. Storage rooms, I know this is a tricky issue and interferes with the perception of operators for free flow, free movement, but storage room, cold room should be closed as much as possible. We can do these calculations. We would underestimate how much additional cooling load we induce if we allow free flow of warm air into the cold storage. So whenever possible and whenever feasible, we should use at least these lamella curtains to separate the cold area from a warmer area, or use quick closing doors to separate these areas. Here we see a small plate-type heat exchanger which is installed after the compressor in a chiller plant, extracting heat from the superheated gases after the compressor. That's why it's called a desuperheater. Again, this is meant to recover heat from the cooling cycle to generate hot water. About 20% of the heat which else would be dissipated from the condenser, like this, can be recovered as hot water. So actually also the refrigeration cycle can become an effective source of hot water in a very economic way. Because depending on the installation, depending on the size and control we want, this can pay back in a year up to 3 years. So on our terms, this usually is a meaningful investment, especially when designing a new plant, to design for de-superheaters, to support the condenser, to recover heat in a useful way as hot water. Yeah, this is more for the fun of it, but it's a picture with a meaning in behind. You remember we were discussing hot air entering cold area, inducing additional need for cooling. This picture here apparently comes from Africa, from a very hot area. Outside air temperature is 34, 35 degrees. This, in our case now here, is not a dairy, but a fish processing company. So on the other side, where this gentleman is sitting, is a storage room for deep frozen fish at minus 20 degrees. So hot air, 35 degrees, entering cold storage at minus 20 degrees really hurts. Needs a lot of additional cooling. So this here is the loading bay. So from here, the cartons, the boxes with the frozen fish are loaded on the trucks. So it's inevitable that when the truck docks to this bay, hot air enters. The guys here found a very simple but very effective way of sealing the bay against the truck when the fish is loaded. They put old mattresses, they covered them with canvas, and now when the truck comes, it opens the rear door and then packs into these mattresses. And these mattresses seal the truck towards the cold storage, so there is no hot air entering into the cold storage. We have much more effective ways than these mattresses. There are proper foldable docking bays available, rubber cushions, all this is nicely available, and we can do technically much better than these guys, but the principle stays the same. Avoid hot air from entering cold areas. One thing to consider when, especially when buying new equipment, new motors, is the energy efficiency class of motors. And nowadays, when specifying new equipment, it should be a routine matter to specify energy efficient motors, which will save some energy as compared to not efficient ones. Most savings usually from motors we can get from controlling motors properly. We are now looking into pumps, we are looking into fans. Very rarely I will need a completely constant water flow from a pump all day, all night, during all the days. Usually the pump will have to deliver a range of water flows depending on whether it's high production, low production, high season, low season, summer, winter. So I will have to control the water flow a pump delivers or the airflow a fan delivers. How can I control the flow of water from a pump? The usual approach would be to use a valve. By closing the valve, I induce a higher pressure drop in my liquid flow, and this throttles the flow. The pump will more or less continue working the same, but by throttling the flow, I reduce it. And if I need more, I open the valve. This works nicely, but energetically is not awfully effective. The more efficient approach would be to use a frequency controlled drive to reduce or increase the rotations of my motor, thus the rotations of my pump, thus the flow. The impact of this is shown here in this slide. This slide compares the motor power over the range of delivery heads for conventional control versus frequency control for a certain pump. A freshwater pump, 60 kilowatts, which we analyzed years ago in a dairy. You see that these are the percentage of nominal delivery. Here is the motor power in kilowatts. So if I reduce water flow from 100% to 50%, the power of the motor in throttling conditions comes down from 60 to 45. Whereas if I use a frequency controlled drive in the same situation, reducing delivery head from 100 to 50%, the power of the motor would come down to 10 kilowatts. So using frequency controlled drive would reduce power consumption for the same condition to a little bit more than 20% as compared to controlled by a valve. This is a quite typical situation. So whenever on pumps or fans with a capacity of more than 7-8 kilowatts, we need a wider range of operating conditions. A frequency controlled drive will pay in half a year to 1 year easily. And they are available now also for quite big motor sizes. What is wrong in this slide? We're touching here also a very, very generic topic, which is not only true for a dairy, although this picture comes out of a dairy. This way of lighting is not really effective. Huh? Actually, almost everything is wrong here. This is old, thick T8 light bulbs. They could be replaced by T5. There is no reflector, so half of the light actually is radiated towards the ceilings without any impact on the plant floor. And we have not started discussing occupational health and safety, fire protection, all these things, because an installation like this is not possible. This is better. There should be reflectors. Light should be guided to where I need it. And if we are talking about new installations, nowadays we definitely need to discuss LEDs. In outside downlights, floodlights, already today it's a clear decision. LEDs will be much more economical than conventional halogenous bulbs, but also in inside installations. This is a picture from Stuttgart. LEDs become competitive, especially if I want to use the full benefit of control of lights depending on outside light. LEDs become something I definitely need to consider for the future. We have calculated several installations now in the last year where the payback time was somewhere in the range of 1.5–2 years compared LEDs to conventional lights. And in food processing, we need to extend this discussion a little bit, because in cold storage areas, for example, LED has several benefits. With the low power requirements of LEDs, the heat which we introduce into cold storage areas becomes much less. So there will be an additional benefit by reducing the cooling load. And LEDs also have the benefit of not involving any glass tubes. So we can reduce the effort we have to take into unbreakable luminaires. So in food industry, and especially in cold areas, LEDs are actually the choice already now for new installations. The purpose of this here is only to show, because this picture is taken actually in a dairy, in a very small dairy in Nepal, far away on the rim of the Himalayas. And these guys made waste minimization a personal task. So he, for example, put these containers in his plant, small plant. He was employing 10 people for plastic, for paper, for glass, and he recycled everything. And the small message out of this is, if a guy in the Himalaya can do that, we can do it also. There is no need for solid waste to be landfilled. Practically all of what we generate in terms of packaging material, in terms of glass, in terms of cardboard paper, at some point can be recycled. This is leading us to the last slides. After all, a dairy will generate some wastewater. Wastewater treatment is a different topic. We could devote another webinar on different approaches to wastewater treatment in combination with the municipality or as a standalone installation. Just a few remarks what cost-effective ways to treat residual wastewater after implementing all the possible reduction measures. What we definitely should install if we are a dairy is a grease trap to collect fat, not allowing the fat into the municipal sewage system. Can be very simple. Coming back to what we have discussed, the trick in the grease trap is maintenance. Needs to be emptied every now and then, needs some basic monitoring, and maybe something for the future, but more probably on a regional level in a cooperation of companies, food processing companies, agricultural companies with the municipality, is the development of biogas plant, which turn the COD of wastewater into a valuable resource, which is methane, which then can be used for heating or in a cogeneration plant. Yeah, these are some remarks. What all this in the end should lead to is what is called nowadays a circular economy. And this butterfly actually represents the essence of this concept. Basically, the idea of circular economy is to keep all material resources in cycles. In a linear economy, as we have it as of now, we extract resources from the environment, we process them to products, we use these products, and in the end we landfill the products or byproducts. In the concept of the circular economy, the extraction of resources and the landfilling does not exist anymore. Because all the materials, all the biologic materials are kept in cycles. Materials through repairing, maintaining, reusing, refurbishing, biological materials by biogas generation, by soil restoration, by using waste as a fertilizer in agriculture. Let's leave this for the moment as a vision, but basically all these activities which I've described shall fill some gaps in this picture. The guide, the pocket guide which we have discussed, is available. I think you have copies of these. Please use it, please distribute it,